Hello everyone. Thank you for joining us. In today's webinar, we will introduce our 3D electromagnetic simulation solution inside Autodesk Inventor. Our solution specialist will cover different electric problems using static and conduction solvers of EMS software. In addition, the webinar will include the demonstration of software workflow and simulation outputs that can be achieved using EMS for Inventor. Before discussing today's agenda, let me introduce us. My name is Cal and I handle sales and marketing division of our company. My colleague Arvind, who is a senior director of product management and an expert on application topics within the domain of low frequency electromagnetics, will be delivering the technical part of today's webinar. Before moving on, I would like to highlight few points. During this course of presentation, if you have any questions, please feel free to use the chat window to type in your questions. We will answer them at the end of this presentation or will reply to you via emails. A webinar recording link will be sent to all the registrants in few days. Our agenda for today is following. I will briefly talk about our company EMWorks and different package options available within EMS for Inventor software. Then my colleague will present the technical part of this webinar. At the end of the technical presentation, I will talk about various learning resources offered by EMWorks for its software users. EMWorks offers 3D and 2D electromagnetic simulation software as an add-in tool for SolidWorks and Autodesk Inventor 3D CAD. Our company was founded in the year 2000. We have a vast sales network in the form of 2 offices and a global reseller channel. We provide our solutions and services directly or through a reseller in America, Europe, and Asia Pacific region. Our company has a strong research and development team with years of experience in the field of electromagnetics. As you can see on the screen, we have 2 office locations. Our headquarters is in Montreal, Canada, and we have another office in Germany. EMS for Inventor offers electrical and magnetic solvers. In addition, multiphysics add-on such as thermal analysis is also available with this product. EMS software is available in 3 packages: electric, magnetic, and professional. Arvind will talk about electric solvers during the technical presentation. Let us briefly touch upon licensing structure offered by EMWorks. We offer 3 different programs: commercial, academic, and startup. Each program has its own benefits and requirements. Within commercial program, we offer perpetual license, while in the rest of the 2 programs, our licensing structure is usually annual based. The topic for today's presentation is electric simulation inside Autodesk Inventor. My colleague Arvind will discuss about 3 different electric problems: 3-phase cables, high voltage insulators, and automotive fuse. I would now request my colleague Arvind to take over and present the next part of this webinar. Thank you.
Thank you, Cal. In this technical part of the presentation, I will cover the electric solvers in EMS for Inventor. We will take 3 examples. The first example will be that of an automotive fuse, and we will use the electric conduction and the thermal solver inside EMS for Inventor. Next example, we will see an insulator assembly where we will use the electrostatic solver. And finally, we will tackle the 3-phase cable problem using the AC electric solver. In this example, we will study an automotive fuse using EMS for Inventor. let me explain the physical construction of one such fuse. So, how does a fuse operate? First of all, there is going to be a small potential difference that is going to drive current through the fuse. So there will be a potential difference between this end of the fuse and this end of the fuse. As a result, there will be some current that will flow through this fuse. As long as the current value stays within the normal operating conditions of this fuse, the fuse will be fine. But what happens if the current exceeds the capacity? If the current exceeds the capacity, the fuse is designed to fail around its weakest point. What do I mean by fail? What I mean is that the temperature that is generated due to the current flow around this weakest point of the fuse increases so high that it melts the fuse locally in this region. So in this particular example using EMS for Inventor, we will see how the flow of current due to a potential difference affects the temperature distribution in the fuse. To do that, we will actually use the electric conduction study in EMS for Inventor. Here we have created what is called as a electric conduction study. I have the ability to couple this study with a thermal simulation. So I have coupled this study with a transient thermal simulation, and we are going to study the functioning of the fuse for a period of about 10 seconds with a time increment of half a second. Next, we will define the material of the fuse. The fuse typically is made of materials such as zinc. So I'm going to use zinc as the material for the fuse. EMS for Inventor has a very convenient way of organizing its materials. Here we see all the material properties associated with zinc. The users can actually edit the material and input their own properties. The main salient properties are the thermal conductivity, the electrical conductivity, the specific heat, the density of the material. Next, we will have to apply the potential difference. Here, I'm going to actually apply a voltage at one end of the fuse. So here I'm going to keep this end of the fuse at 2 volts and go to the other end of the fuse, in this case this end of the fuse, and input a voltage of 1.8 volts. As a result, we will maintain a potential difference of 0.2 volt across the fuse, which is very typical for a fuse that you see here. And finally, because we are coupling it with a thermal simulation, it is a good idea to see how the convection happens. So here we have included all the outer faces of the cube, and we have specified a convection boundary condition. And the ambient temperature is around 300 Kelvin, and it is convecting to the ambient in a natural convection mode. One can also ask EMS for Inventor to compute the effective resistance of such a structure. So here I have requested the program to compute a resistance between the inlet and the outlet phase. So now the setup of the automotive fuse simulation is complete. Now we can take a look at the results. And before we go to the results, I want to mention that EMS is actually a finite element simulation program, and So the first step in the simulation is creating what is called as a finite element mesh. As you see here, EMS automatically creates an optimal finite element mesh, which is then solved so that we can take a look at the results. So let me go ahead and take a look at the results. What kind of results are available for us when we do such a study? The first thing that you can do is you can visualize the density of the current. And this is important because this density of the current is what determines the temperature, and it will also determine the failure of a fuse. So you can see the current density and the respective values in the color chart here. So obviously the current density in the weakest point of the fuse is very high, denoted by the red arrows and the green arrows. And in other points where you see blue arrows, the current density is low. So this vector plot gives you both the magnitude and the size of these vectors determine the current density. In addition to the current density, one of the most important things that we are looking for is the temperature distribution of the fuse. Here, I am going to visualize the temperature distribution in the fuse after a particular time step. So if I edit this definition, you can study the temperature distribution in centigrade or in Kelvin or in Fahrenheit of the fuse after a particular time step. So here, after about 1 second, we study the temperature distribution in the fuse. So that's time step 3 and the time is 1 second. We can also increase the time step so we can study the temperature distribution at various time. So this is the temperature distribution of the fuse after about 2 seconds. Okay. And you can see that the temperature is about 485 degrees centigrade, which is close or actually exceeds the melting point of zinc, which is about 420 to 450 degree centigrade. So you can see that under this operating condition, where there is a potential difference of 0.2 volts, the zinc actually melts within 1 to 2 seconds, which is what you would expect from the performance of such a fuse. Finally, you can actually study how the temperature evolves as a function of time. Here I have selected a particular sensor location, and I can actually study how the temperature evolves as a function of time at this particular location. So I can plot the function of temperature as time evolves. So this is a plot of the temperature of the sensor location as a function of time. You can see how within the first 2 seconds the temperature reaches close to 400 degrees C at the sensor location. And if you have some specification about the functioning of the fuse, that it needs to melt within a couple of seconds, and you can be sure that the dimensions that you selected for the design of the fuse meets your specification. Finally, let us go to the result table where we can study the following. We can study the dissipated power in the fuse, and that's close to around 375 watts. And finally, we can also study the resistance between the input and output of the fuse. So the effective resistance is also given by the program. So in this example, we saw how EMS for Inventor can be used to study the design of an automotive fuse using the electric conduction solver. Now we will take a look at the electrostatic solver, and we will use the insulator assembly. In this example, we will study an insulator assembly and the objective is to find out the electric field in the insulator as well as the air surrounding the insulator. Now, if you look at the model, we have two disc insulators that are made from beryllia. We also have a conductor, aluminum, which is in contact with a high voltage power source, and the voltage is 80 kilovolts. And at the top, we have another aluminum that is connected to a grounded plane. The objective of this simulation in EMS for Inventor is to find out the electric field distribution in and around the insulator arrangement. To do that, we have created what is called as an electrostatic study in EMS, and we have also requested the program to compute the breakdown voltage. Once the study has been created, we have defined the materials for the various components. The two discs, they are made of beryllia, and then the other conductors are made from aluminum. And finally, we have an air geometry that I've hidden and I'm going to show you right now, which actually covers the entire model. So if I turn on the transparency, you can see that the entire geometry of the insulator is encapsulated inside this air geometry. Next, we will apply the boundary conditions, namely the voltages. So we are going to take the bottom conductor, and that is in contact with a high voltage 80 kilovolt line. So let us apply a 80 kilovolt voltage to the bottom conductor. To the top conductor, which is grounded, we apply a 0 volt ground potential. And finally, the conductor in the middle is really a floating conductor. It is not in direct contact with either the high voltage source or the grounded source, whereas it is in contact with the two insulators. So we apply what is called as a floating conductor for all the conductors in your assembly that does not have a particular value of electric potential. Let me go ahead and hide the air geometry. And this actually concludes the application of boundary conditions. Now we can go ahead and take a look at the results. The first result that we are interested in looking at is the electric field, a section plot of the electric field through the insulators. As I zoom in, you can see the value of the electric field. The maximum value of the electric field is around 1.45 million volt per meter. And you can see the distribution of the electric field in the insulator. We also requested the program to compute the safety factor, and here you can see the safety factor distribution. The way to interpret this chart is that anything that is yellow and red means that it is dangerous and it is close to the breakdown voltage. As we see, most of the regions or almost all the regions in the insulator are in the bottommost blue. So we can be very sure that the insulator design ensures no breakdown when it is connected to a 80 kilovolt voltage source. Now we can do some interesting things. We looked at the electric field and safety factor distribution in the solid parts. Now let us go ahead and make the air geometry visible, and I can go to EMS and then I can plot the electric field distribution when you also have air region around it. Notice that the breakdown can occur not just in the insulator solid component but also in the air surrounding these components. So it's important to be able to visualize the electric field distribution not just in the solid components but also in the air region surrounding them. And this plot gives you a good idea of how the electric field is distributed in the air region. Now, another thing we can do is we can isolate the air and look at only the air. And I go back to EMS and I double click on the electric field plot. Now, this will hide all the solid components and we are able to only look at the electric field distribution in the air region. Now you can see that the maximum electric field is right in the bottom and right in these corner areas, and that value is around 1.2 million volt per meter. We know that the air breaks down at 3 million volt per meter, and as a result we can be sure that the breakdown of the air has not occurred for this operating voltage. You can also take a look at the safety factor. Here is a section plot of the safety factor with only the air shown. And you can see that there are no regions in yellow or red, and so most of it is in the light blue area. And you can be sure that this design is safe. In this final concluding example, we will take a look at the three-phase cable using AC electric solver. In this final example, we will see how an AC electric simulation is used to study a high voltage three-phase cable. The study that we defined this time is called an AC electric study. Here we input the frequency, in this case 60 Hertz. Next, the usual steps follow. Here the three conductors are made from copper. The insulator that we have used is solid PTFE. Let me edit the material. And you can see its relative permittivity 2.1 and its dielectric strength is around 19.7 million volt per meter. And finally, the outer metal is made from aluminum. Let us see what kind of voltages we apply to the three conductors. The three conductors, they carry AC current with an RMS value of 10,000 volts. So the first conductor carries 10,000 volts and the voltage phase is 0 degrees. Because it is three phase, when we apply the boundary condition for the second conductor, we apply a phase of 120 degrees. And finally, the third conductor has again 10,000 volts potential and the phase is 240 degrees. Last but not the least, we take the aluminum outer conductor and then apply a ground potential of 0 volt. We have run the simulation and we can take a look at the results. The first result that we will be looking at is the electric field distribution. Here you see the electric field distribution in the insulator. The maximum value that you get is around 3.6 million volt per meter. But if you recall, the insulator has a breakdown voltage of 19.7 million volt per meter. Hence, the 3.6 million volt per meter is well within the breakdown voltage. This is illustrated by the safety factor plot. Here, the safety factor plot shows you which areas are vulnerable for breakdown. You can see that most of the areas are either in the dark blue or in the light blue section. And if you recollect from earlier example, the way to interpret the safety factor is if you get regions in the red, then those regions are vulnerable for breakdown. Because we don't have any, so we can safely conclude that this design of a three-phase cable can handle 10,000 volt RMS three-phase. Last, we can take a look at the potential distribution in volts, and here you can see the distribution of the potential. So the maximum potential is 10,000 volt RMS, and we also see a 0 volt ground potential applied to the outer conductor, and the distribution of the potential is very symmetric about the three conductors as expected. So, in this section of the technical part of this webinar, we saw three important examples covering the electrical solvers in EMS for Inventor. Now I will hand over the session back to my colleague Cal. Thank you for watching this.
Thank you, Arvind. Let us do a quick recap. EMS for Inventor offers electrical and magnetic solvers. In addition, if you require to compute temperature distribution in your model, we offer thermal analysis add-on as well. EMS software is available in three packages: electric, magnetic, and professional. To get information on software pricing, you can connect with me after this webinar. This slide represents a small subset of capabilities offered in EMS software. I will give a brief overview of three main capabilities: magnetic and electric solvers. Magnetic solver can help a user to analyze magnetic fields, forces, eddy currents, losses due to time harmonic currents, and electric solver allows you to analyze electric fields, conduction currents, safety factor, breakdown voltages due to time varying or stationary electric fields. Number two is thermal analysis. Through this multiphysics add-on, you can calculate temperature distribution, temperature gradient, and heat flux in your model. Number three is parameterization. This capability enables a designer to run multiple what-if scenarios and determine a best design. EMWorks offers various free learning resources. With the software purchase or trial, users can access the demo viewer section of the software, through which they can access many predefined model examples and tutorials. In addition, we post application notes, blogs, and videos on our webpage and social media channels regularly. We also offer paid customized training sessions to all the users of EMWorks software. I encourage everyone to try our software and experience its capabilities. Upon trial request and user qualification, we offer 2 weeks of free access to the limited version of the software. In this limited version, users can access many predefined model examples and tutorials to learn about the software features and capabilities. To request for a trial license, visit our webpage www.emworks.com. Go to our Contact Us page, fill in your information, and submit your request. One of our representatives will reach out to you soon. I would like to thank you all on behalf of EMWorks for participating in this webinar. Feel free to contact us after this webinar to get more information on this product. Thank you.